Today we're going to start talking about forces, which are very important when talking about mechanical action in biomedical systems. One motivation for this, again, going back to a particle system we looked at a few years ago, if you have particles hitting each other, you need to figure out the forces, at what force they are approaching each other. Are they coming in too fast or too slow? And if they come in too hard, they may break the particles apart. If they come in at the right speed, they may actually coalesce to make a larger particle. And there are models out there where you can look at this granulation phenomena. But there's lots of applications in biomedical engineering looking at forces and trying to deal with the mathematics related to forces. So we're going to talk about two-dimensional vectors. And a coplanar vector can be fully contained within a single plane. So if you consider x and y axis, those are coplanar because they're inside the x and y plane, or z equals 0, let's say, and the coplanar vectors are basically all inside that plane. So these are usually, the components of this are called rectangular components. So the value of a vector in the x direction and the value of the component in the y direction represent that vector. Now, we often look at 2D problems because the math is a lot easier than trying to do 3D. So we try and figure out how to resolve or simplify our models, our problems into a two-dimensional application. It's just simpler, and that a lot of times the components in the third dimension are small, or they're just repeated for basically what ends up looking like an infinite amount of time or an infinite amount of values. So 2D analysis can often be adequate for at least a first pass in many of our engineering problems. So we have to learn to resolve these vectors into components using the x and y axis system. So if we have a vector, this big vector f, capital F, which is a vector, it's going to have, if it's a two-dimensional vector, it's going to have an x component, the length of this triangle, and the y component, the length of this triangle. Now, we have to figure out how to determine f of x and f of y. And we're going to use the unit vectors I and j to designate the x and y axis, just like x, I, j, k, or x, y, and z. So one thing we're going to talk about is adding these vectors. This force vector f is really the sum of fy and fx. We're going to talk about adding vectors head to tail. So you could take this fy vector and move it over here and add fx plus fy to resolve f. The same way you can take fx and move it up here, but add the tail of fx right here to the head of fy, so that fy plus fx resolves to be f. We can have a rotated basis. We could have our vectors, and in some cases we may want to swap everything around to a different plane, basically, so that we have I and define j this way. I and j are always going to be perpendicular together, so as long as you define what I and j are, you should be in good shape. Effectively, this is another way. You may not, instead of changing all of your coordinates around, if everything's just slightly rotated, you can use the new coordinate inclination. Now, as I said, we have to learn to add vectors head to tail. In this case, if we know A and we know theta, we have to determine AX and AY. So the cosine of theta times A will give you the AX value when the theta is defined this way, and the sine of theta times A will give you the AY value when theta is defined in this manner. So this is the size of the component in the y direction, and this is the size of the component in the x direction. We don't have to know the angle for these two forces because the AX value, the component in the x direction, is along the x axis, and the AY value is along the y axis. So when we write A, the overall A, we can write as a force where it has a number times the I value and a number times the j value. So I is the unit component in the x direction, and j is the unit component in the y direction. So we have AX and AY. What do we want to do? We want to be able to multiply or add together three forces that are acting on one specific point. So if we want to add F1 plus F2 plus F3, we need to resolve each vector into its components. Then the step 2 is add up all the components for the x's and all the y components. These are giving you the resultant vector. So if you add these three forces together, you get the fx for F1, fx for F2, and fx for F3, and that's all the x components. The same thing for the y components. Fy for F1, Fy for F2, and Fy for F3. and then we find the magnitude and angle of the resultant vector. Now, something we hadn't talked about is negative components. In this case, F1 is in quadrant 1, so X and Y are both positive. F2 is over in quadrant 2. Fx is going to be a negative component, and F2 is going to be a positive component. And here, F3 is going to be a positive X component, and Fy is going to be a negative component. So we have to break these three vectors down, F1, F2, F3, into F1x, F1y, F2x, which is negative, F2y, F3x, and F3y. And here I'm showing you F2x is a negative number. So F2x is a negative value in this negative direction. Here F3y is a negative value. So you sum these all up to get a value. For the x, the resultant is the sum of these three x components. The resultant y value is the sum of these y components. So you have to be, this is what we're going after, the values of x, the values of y. Once you know these values, then you can back out the angle and magnitude for the resultant vector. So what does that mean? Well, if we have this, if our resultant vector is in the first quadrant, we know it's the size is this function, which is basically the distance from the origin. The resultant vector squared in the x component, and the resultant y component squared. So square root of that gives you the length of that triangle. And if we know opposite over adjacent, or if we know how to use arctan for the ry and rx. So that's how we back out what this theta value is. We can also use similar triangles to try and determine the components in the x and y direction. So if we know the slope of the force, we can back out the values for the component vectors just from that information, either using arctan to back out the theta, the actual angle, or we can try and back out, if we know the slope, that's the rise over the run, so we know B and A, or we can assume values for that, and then you can back out what C is. You can back out all of these things if you understand how to use geometry and triangles. So you may not have the angle specified, you may only be given the slope of this resultant vector, and you can use formulas like these, similar triangle arguments, to find the x and y components depending on what you don't know. In 3 dimensions, you can do components in 3D, and COMSOL will do that for you in many cases, but again, it makes it very complicated, and doing the math for 3-dimensional vectors is more complicated because you don't just have an angle in the x and y plane, you also have an angle in the z direction. So how you define that and how you apply that is a little bit more difficult to deal with. The magnitude's the same. It's basically the x component squared plus the y component squared plus z component squared, the square root of all of that. But defining all of the other geometry that goes along with it can be a little bit of a messy nightmare in some cases. You have to deal with all these different angles. There's different standards for coming up with these, but you can have an angle, alpha and beta and gamma. There's different ways for backing out what alpha, beta, and gamma are if you know these direction cosines. So the other thing is the angles can't be independent because you know that cosine alpha plus cosine beta plus cosine gamma, all those squared, is going to equal to 1. So you have to satisfy that trig identity. However, once you have the components in the x, y, and z direction, it just works the same way as in 2D. If you know all the x components, the y components, and z components, they just add up to find the x, y, and z. So if we have these values, we can just add ax and bx, ay, by, az, bz to get a plus b. You can also subtract vectors if you want to. Now, if we have an example problem, we have a femur where we have a force acting on this. And you can come up with a free body diagram, which is a simplified sketch for all the forces. So maybe there's a force pushing on this part of the femur, and there's a weight of the femur pushing down. So the body is pushing this way, and the weight of the femur is pushing down, and there's a normal force pushing back up from the bottom. So these three forces are acting on this one body. The net force is going to add F1 plus F2 plus F3. So we have to break that into components. Break F1 into the x component and the y component. F2 is only down, so it only has a negative j component. And F3 is only up, so it only has a positive j component. And we found the x component based on the size of f1, for the x component for f1 based on the size of f1 and the angle that we know it's making with this value. And same for f1 and the y component. So we have these values. We put numbers in for these values. We add the components, so we know that we have only this value. The only one up here in these components that has any x component is this value. We have 3 y components that are in the j direction. So we can figure out it's basically negative 70 I minus 40.7 j. So once we have that, we have to figure out the angle. We know it goes down 40 and over 70, or over 70 and down 40. So that's the result of f1 plus f2 plus f3. So we can find the magnitude of that force vector using the magnitude formula. You plug in 70.7 and 40.7, you square it, add them, square root, get 81.5. That seems reasonable. And once you know fx and fy, you can put it in the arctan and figure out that it's 60 degrees, which sort of makes sense. If we put all these two vectors together, it seems like the resultant vector may be 60 degrees when we measure it in this direction. You could alternatively count this from the x equals 0 as 180 plus 30, depending on how you set up your trig. So there's different ways of reporting theta, and generally I try and be very clear about how I'd like you to specify what theta is. And that's all for today.